Of the stuff we were talking about yesterday. MVT for derivatives. Right. So how could we deal with a problem like this one? This is really cool that we can. When an object is removed from a furnace and placed in an environment with a constant temperature of 90 degrees Fahrenheit, its core temperature is 1500 degrees Fahrenheit. 5 hours later, the core temperature is 390. Explain why there must exist a time in the interval when the temperature is decreasing at a rate of 222 degrees Fahrenheit per hour. What would I do? Helps to always think in terms of a graph. The more you can do that in math, the better off you're going to be. So if I were going to draw a graph here, what would the graph look like? What would the axes be in my plane? Okay, y-axis would be temperature in degrees Fahrenheit. Good, okay. So we'll call that capital T measured in degrees Fahrenheit. Okay, x is time in hours. Good. So small t hours. Okay. What do we know about our plane? Anything? It's decreasing. Do we know any points? Okay, good. Okay, so we know that starts off at 1500. So at time 0, right? That'd be when we start the clock. We're up here at 1500. What else do we know? Okay, 5 hours later, it's 390. So at t equals 5, down here somewhere, we're at 390, right? Okay, so we don't know how the curve progresses from the start of the interval, which is at 0, to the end of the interval, which is at 5. Who knows? I know. I can tell you what it's doing. It's following Newton's law of cooling, and it's doing this. It's kind of doing that. Okay. What about this other part? What about this 222 decreasing at a rate of 222 degrees Fahrenheit? Where's that number come from, do you suppose? Well, okay. I mean, we're going to go there, but we're not there yet. Explain why there must exist a time in the interval when the temperature is decreasing at a rate of 222 degrees Fahrenheit per hour. That 222 it sounds like they just pulled that out of the air, but they didn't. That comes from something specific. What do you think it might come from? What do you think? You got an idea, I can tell. What are you going to say, Ashley? I think you know. So we're talking about the MVT, right? Think about how MVT could apply here. If the function is smooth, so continuous on the closed interval, differentiable on the open interval between the endpoints, then there exists at least one place where the slope of the tangent line is equal to the slope of the secant line. Slope of the secant line always represents average rate of change, right? It's the rate of change over some interval.
So is 22 per hour then?
What do you think? Let's see. So if we start off with what's our average rate of change here? So if we try, where am I going to do this? We'll do this over here. Okay, so f of 5 minus f of 0 over 5 minus 0 equals what? Well, f of 5 is what? For us. I mean, really for us, it's t, it's not f. So it's 390, isn't it? Right? What's t of 0? 1500 over 5 minus 0 is 5. What do you suppose 390 minus 1500 over 5 is going to be? Yeah, that's negative 222. And the units would just be degrees Fahrenheit per hour, right? Because we're units of temperature over units of time. So that is the slope of the secant line connecting those, right? Slope of the secant line is negative 222. So do we meet the criteria for the mean value theorem here? Is F, which is really capital T, right? Is T of T continuous on our interval from, well, what's A to B in our case? Yeah. Is it? For it not to be continuous, what would have to happen to the temperature? Well, no, I mean, so continuous means that I can think in terms of the graph. It means that I can put my pen on the board and I can graph the temperature curve without ever picking my pen off the board. Okay. For it not to be continuous, what would have to happen to the temperature? What would cause me to have to pick my pen off the board? What would it have to be? A jump in temperature, yeah. The temperature would have to spontaneously or instantly jump from one temperature to a different temperature. Okay, does it ever do that? No, wouldn't you agree that the temperature has to go through an infinite number of different values between 1500 and 390 when it falls? Like it's a continuous change. It's not like it's ever going to just spontaneously jump from 1500 to 1400 in the blink of an eye. It can't do that, right? It has to go through, as it cools, it's going to go through every possible temperature starting at 1500 and ending at 390. Agreed? Okay. There aren't little quanta of temperature. Well, there might be actually, but we're not considering any of that stuff. It's not like there are these discrete values temperature can have. It's a continuous distribution of temperatures, right? So yeah, it makes sense because this is a physical process. You can't just, it'd be like saying if you were walking up a hill, and we did something like this with the intermediate value theorem earlier in the year, right? We said to go from the bottom of the mountain to the top of the mountain, you have to go through every altitude between the start and the finish. You don't spontaneously just beam yourself up to a different altitude. Same thing with temperature. So we checked that box, don't we? Is it differentiable? It is. It is different. Yeah, what do you think? Oh, okay. So it is differentiable because the rate at which the temperature is decreasing is smooth, right? It's never gonna like spontaneously jump from. You're not gonna have a sharp corner in your temperature distribution, right? It just doesn't make sense that that would happen. So yeah, it's got to be. We have to meet those criteria because this is a physical process, and so therefore we meet the criteria. So MVT guarantees that there's going to be at least one place where the slope of the tangent line equals the slope of the secant line. So it must at least one place have exactly that rate of change. It turns out there would be only one place because the curve would, the rate of change of temperature is going to decrease with time. Absolute value, I guess, of that. It's gonna start off cooling rapidly and end up cooling less rapidly at the end. Okay, that makes sense. Okay. Okay, so all right. So that's the mean value theorem for derivatives. Okay, now I want to show you guys the mean value theorem for integrals. I wonder, let me pause this.